Airborne weather radar is used to provide pilots with information regarding weather ahead, cloud height, terrain height, and to provide a position fix. The radar information can be displayed on a dedicated unit or shown in combination with the aircraft route on the EFIS navigation display. Information on cloud formations or terrain features is displayed as a range from the aircraft and a bearing relative to its heading. The presentation, in ascending order, is in green, yellow, red and magenta, although older units may be in monochrome. In the weather mode, the colours represent the increasing variations in rainfall rate from light to very heavy. Green represents the lightest rainfall and magenta the heaviest, and usually indicates the presence of turbulence. For ground mapping, the green represents flat ground or water, whereas red represents large solid objects, such as mountains. The component parts of airborne weather radar are the transmitter-receiver, the antenna, the indicator, and the control unit. As with most mapping radars, the echo principle is used to detect slant range, and the searchlight principle is used to detect relative bearing. The radar beam is produced by a suitable antenna, usually a phased slot flat plate antenna. In older equipment, two types of beam are produced. The conical or pencil-shaped beam is used for weather and long-range terrain mapping, whilst the co-secant squared or fan-shaped beam is used for short-range terrain mapping. That is, out to 60 to 70 nautical miles. In modern equipment, only one type of beam is used for both functions, and the scanning angle is changed as required. The antenna is normally gyro-stabilized, both in pitch and roll, to the earth horizontal, in order to keep the scanner horizontal as the aircraft banks. Otherwise, during the bank, the picture would be degraded, as one side would be too bright, and the other side would be blank, as the energy went out into space, never to return. The pencil beam has a width of between 3 degrees and 5 degrees, and the exact width can be calculated using the formula 70 times wavelength divided by the diameter of the antenna. So, given a wavelength of 3 centimeters and an antenna diameter of 45 centimeters, the beam width is 4.7 degrees. It is desirable to have as narrow a beam as possible for better definition. For example, to distinguish between two cumulonimbus clouds. Narrow beams are produced by having larger antennae, but as this is not possible on an aircraft, shorter wavelengths or higher frequencies have to be used instead. The choice of radar frequency is largely determined by the purpose of the radar, which is to detect large water droplets and wet hail. These have a diameter of about 3 centimeters, and so the ideal wavelength is the same size. A typical frequency used is 9375 MHz, which produces a wavelength of 3.2 centimeters. A higher frequency would produce returns from smaller droplets, whereas a lower frequency would fail to produce sufficient returns to highlight the area of turbulence. Here, we see the coverage for a 3-degree beam at various ranges. The equipment is designed to detect those clouds which are likely to produce turbulence, to highlight the areas where the turbulence is most severe, and to indicate safe routes to avoid them where possible. The size and concentration of water droplets in clouds is an indication of the presence of turbulence, other than clear air turbulence. The shorter the distance in continuous rainfall between light and strong returns, the steeper the rainfall gradient and the greater the likelihood of turbulence. Here we see the reflective levels of different precipitation types. In color weather radar systems, the weather targets are color-coded according to the intensity of the rainfall. We have seen that the areas of greatest potential turbulence occur where the colors are closest together and also where certain shapes are depicted, indicating hail activity. These shapes are the letter U, a finger, a scalloped edge, or a hook. Both monochrome and color radar have similar basic functions, but color radar has some additional features which we will look at later in the lesson. Let's start with the monochrome control unit and the power switch. In the on position, the antenna is automatically stabilized in both pitch and roll and aligned with earth horizontal. Switching to the stab off position will lock the antenna to the fore-aft axis of the aircraft. The range switch selects the maximum distance to be scanned, usually up to about 150 nautical miles. Initially on the ground, standby should be selected so that the scanner is not operative. Radar beams can be harmful to humans, and strong returns from large buildings or vehicles may damage the equipment. Tilt control enables the radar beam to be tilted from the horizontal within 15 degrees up or 15 degrees down. In the horizontal plane, the beam can scan up to 90 degrees either side of the nose. When you are clear of hazards, but still on the ground, the maximum up tilt and the pencil beam should be selected. Once airborne, for weather detection, the tilt angle is raised to avoid ground returns. Due to the curvature of the Earth, the tilt should be higher when the selected range increases or when the aircraft descends to a lower altitude. The function switch has 4 positions: map, manual, weather, and contour. In the map position, the radar produces a mapping beam. In order to obtain an even presentation of surface features, the transmitter power in older equipment is progressively reduced as distance decreases. This reduction in power is a function of the cosecant of the depression angle, hence the name cosecant squared beam. The dimensions of the cosecant squared or fan beam are 85 degrees deep in the vertical plane and 3.5 degrees in azimuth. Signal amplification is adjustable via the manual gain knob. The downward tilt is adjusted for the best target presentation. Little energy reflects from a calm sea, sand, flat terrain, or snow, which masks ground features, and so returns are weak. Bright returns will be received from built-up areas and mountains, while ice produces jagged edges. Flight over high ground can produce a false image of a series of lakes due to radar shadow caused by the mountains. In older equipment, The other use of the mapping function is to identify a ground feature and thereby obtain a position fix. The display will show the range, in our example 13 nautical miles, at slant angle, and a bearing of 30 degrees left of the nose. From this information, we can calculate the true bearing to the feature, so that it can be plotted on a chart. Let's say that an aircraft is at a height of 42,600 feet on a magnetic heading of 216 degrees. Variation is 17 degrees east, so the aircraft is on a true heading of 233 degrees. As the feature is 30 degrees left of the nose, we deduct this from the aircraft's true heading of 233 degrees. So the feature has a position that is 203 degrees from true north. We want the true heading to the feature, which is the reciprocal of 203 degrees, namely 023 degrees true. The other calculation which can be made is to find ground distance to the feature using the Pythagoras theorem, namely that in a right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. The minimum and maximum mapping range depends upon the aircraft's height and the type of terrain, but minimum range is about 15 nautical miles and maximum about 70. Beyond the maximum range of the fan beam, the pencil beam is used by selecting the manual setting. In the manual setting, the pencil beam is selected for cloud detection and terrain mapping beyond 70 nautical miles. Manual gain is available. The weather setting is the usual setting for cloud observation. Manual gain is not available, but an automatic gain control is operative, also called the swept gain facility. This ensures that the intensity of the display is independent of range up to about 25 nautical miles. So, a small cloud at 5 nautical miles does not give a stronger return than a large, more dangerous cloud at 20 nautical miles. The main purpose of weather radar is to enable the aircraft to avoid bad weather. So, it is good practice to adjust the tilt control away from any terrain and to scroll through the distance settings to obtain as much advance warning as possible. Pilots should be aware that it may not be possible to map the area behind heavy rain, which may be hiding unpleasant surprises. The height of clouds is important, so that the pilot can decide whether or not he can climb above the bad weather. The procedure is to move the tilt control up until the returns from the cloud just disappear from the screen. The tilt angle and range of the cloud are noted. The center of the beam, when not tilted, represents the horizontal aspect of the aircraft. This represents the horizontal. Let's now put in a cloud 45 nautical miles in front, with its top slightly above the aircraft's level. When tilted up to just clear the cloud, the tilt angle represents the angle from the aircraft horizontal to the center of the beam. Let's suppose that the top of the cloud is 1 degree above the aircraft horizontal. The beam width is 5 degrees. As we are measuring from the center of the beam to its bottom, we have to deduct half the beam width from our tilt angle in order to calculate the angle between the aircraft horizontal and the top of the cloud. The simple way to calculate this height is to use the 1 in 60 rule, shown here. The height of the top of the cloud above the aircraft horizontal is the tilt angle, minus half the beam width, times the range, times 100 feet. Let's add some figures. An aircraft is at 35,000 feet. The range to the cloud is 45 nautical miles. The beam width is 5 degrees, and the tilt angle is 3.5 degrees. The top of the cloud is 4,500 feet above the aircraft, and therefore 39,500 feet above AMSL. The last of the function switch settings is the contour setting, which applies only to monochrome systems. It portrays in black the areas of most likely turbulence, like red and magenta on color radar. Modern color radar displays may be on a dedicated screen or shown on an EFIS display with other information. The buttons used for selecting functions are Weather, Weather plus Turbulence, which is shown in magenta, Variable Gain Control for the mapping function. The gain control is automatic in all other modes. The test mode displays the color pattern for the pre-flight serviceability check. The hold button allows the display to be frozen, so that when the button is released, the new position of the storm can be seen. The target alert button alerts the pilot to a storm return of contour strength. If no such clouds are present, the screen shows a yellow T in a red square. If a contouring cloud is present within 60 to 160 nautical miles and plus or minus 15 degrees of heading, a yellow symbol TGT flashes on and off within a red square. The word fault flashes on the screen if there is a power or transmitter failure. The word wind shear can be displayed on modern color radar equipment when appropriate. Let's summarize this lesson. The frequency used is 9375 MHz because it gives good returns from large water droplets and heavy precipitation. The color gradation indicates the water droplet size. Green is the smallest, then yellow, red, and finally magenta, which is the largest. The scanner is stabilized to the Earth horizontal in pitch and roll. Turbulence is indicated either by a steep color gradient or by a magenta coloration. The relative cloud height in feet is given by tilt minus half beam width times range in nautical miles times 100. The map mode gives a cosecant squared beam, which is fan-shaped, out to 60 or 70 nautical miles. It shows large areas of ground ahead of the aircraft. For ground mapping at greater ranges, the conical beam should be used. When checking the equipment prior to flight, check that the scanner is not pointed at buildings, personnel, vehicles and aircraft. Then select conical beam and maximum up tilt.